Hi, hello, good morning, good evening, and thank you so much for joining me for this session today. The topic of today's session is a dog versus cat classification using a convolution neural network. So, we would be designing a convolution neural network and we would be feeding it images of dogs and cats, and the model would predict that if it's a dog image or if it's a cat image. So, in my opinion, this session would be helpful for anyone who has heard about CNN, but they do not know the inner workings about it. So, this would be a good starting point for anyone who wants to learn about CNN. Okay, so a little bit about me. So, my name is Jyoti Swaroop Makina. I am a Beta Microsoft Learn Student Ambassador. I am a deep learning enthusiast. I love exploring all and everything about machine learning in general, but specifically in deep learning. Currently, I'm exploring all the neural networks, LSTMs. There is so much to explore. And I'm also a full stack developer. I'm from India. I'm a third year student pursuing artificial intelligence and machine learning from Heritage Institute of Technology. And a few of my hobbies include playing football, watching movies, and I'm an ardent book reader. Okay, so this is what we are going to cover. I just have prepared a few slides. After we cover those slides, there's a little bit of theory. We can straight away jump into code. So these are the topics that we are going to cover today. We will talk about first what a CNN is. I would give a brief introduction about CNN and how they aid in image processing and pattern recognition. A very important point to note before learning any new technology is why did that technology come about? Like, what was the reason for the invention or the development of that technology? So, we will talk about why can't we use ANN and why there was the necessity for CNN to come about. And then we would talk about the typical CNN architecture, like what are the different layers in a CNN model. With that out of the way, then we'll move to various CNN applications, and then we would dive straight into the code. Like I said, like I promised, we just have a few slides, a little bit of theory, and we'll dive straight into the code. Okay, introduction to CNN. So this is how a typical CNN looks like. I know this can be very daunting. When I first started learning CNN, it was daunting for me as well. So there are many layers here, but what's important to focus is this layer. Like, this dense layer is nothing but what you have been using in artificial neural networks. So it's just this artificial neural network. In CNN, these layers are added, the ones that can see in these colors. So these layers are added in CNN. So what are these layers? These are the convolution and pooling layers. We'll talk about them a little later. So first of all, what exactly is a CNN? So as the definition states below, CNNs are also known as a QuantNet. They are a special kind of neural network for processing data that has a known grid-like topology, like for time series data or images, which are 2D. So any data that has a grid-like topology, you can use a CNN for it. So in 1D, the example is the time series data, and for 2D, those are typically images. So why CNN and why not ANN? Like, why can't we use ANN with image data? Like, this is the typical ANN architecture, right? We have the input layer, then we have the much dreaded black box. We have the hidden layers here, and we have the output layer. So the question is, can we use ANNs on image data? What do you guys think? So we can use artificial neural networks with image data, but they have a few drawbacks. So the first drawback is high computation cost. So if I go back, so if we consider this little image of Tweety here, so let's take an example that this image is of size 40 by 40. This is a 40 by 40 pixel grid image, which is a very low resolution image, right? So we have 40 cross 40 image. And let's for now forget that we have any of these layers here, right? So let's say we're feeding this image directly into the ANN. That is the artificial neural. So what would be the steps? First, we would convert this 2D grid structure into a 1D, one-dimensional array. That is what this flattened layer does. So flattened layer basically converts a higher dimensional array to a 1D array. So we would convert this 40 cross 40, which is 1600, and we would convert into this 1D array. So we are feeding this. So this layer that you can see here, it has 1, 2, 3, 4, 5, 6, 7 neurons here. So consider this having 1600 neurons. So the input layer would be of dimension 1600 cross 1. And then we are feeding it into this layer, the first hidden layer, right? In this example, it has 3, 4, 5, 6, 7 here. It has, again, it has 7 here. So it's like 1600. And let's imagine like 7 is a very low number. You will, for instance, be taking much more than 7. So for an example, let's take 100 neurons. So as you can imagine, the weights, so each edge that you're seeing here, right? Each connection that you're seeing, each pixel is connected to a neuron, it has an associated weight with it, right? So this connection that we're doing, 1600 here and 100 neurons here. So the weights in the first layer itself would be 1600 into 100, which is around 1,60,000. So imagine just for the first hidden layer, we have 1,60,000 trainable parameters. And a typical neural network architecture has at least, I mean, you can have many hidden layers, right? It can have 10, 20, or you can have 2, 3 hidden layers as well, right? So with that many hidden layers, you can imagine that the training parameters goes up. So as the training number of training parameters increases, so does the time for calculating for backpropagation increases, and so does the computation cost. That is what I mean by high computation cost. And then overfitting. So overfitting in very simple terms is that the model performs well in training, but it performs bad in testing. So since every pixel is connected to every other neuron, we can have a chance of overfitting when it comes to artificial neural networks. And next is a very important point, which is loss of important information like spatial arrangement of pixels. So what do I mean by that? If we come back to this picture again, as you can see here, these eyes, right? Since these eyes are located close to each other, right? And they have a spatial meaning. If eyes are located very far apart from each other, then that wouldn't make sense, right? The fact that they are close to each other has a spatial meaning to it. But what are we doing? We are basically converting this grid-like structure and we are converting into 1D array. So we are losing the importance of that spatial arrangement. This is a very important drawback that artificial neural networks do not cover. Which brings us to CNN architecture. So does CNN cover all these drawbacks? Yes, the answer is yes. So this is how a typical CNN architecture looks like. Again, this is the dense layer, which is also known as the fully connected layer. And these are the layers that I was talking about. Okay. So we have the convolution layer and we have a pooling layer. Typically, these are the two layers that you're going to add. You can add multiple layers of these. And we also use an activation function, a non-linear activation function like ReLU, which stands for rectifier linear unit, which is basically any negative is converted to zero and positive stays the same value. So this we have the image of the zebra, right? So this input image is fed into a convolution layer. So the task of a convolution layer is to basically extract primitive features from the image. What do I mean by primitive features? Primitive features are basically the edges. As you can see, this zebra is formed of multiple edges, right? This edge here, this tail here, this leg here, this curved edge here, here, this one near to the face. So the convolution layer, the task of a convolution layer is to extract these primitive features, edges. That is the first convolution layer. The next convolution layer, it usually the features that it got from the first layer, it extracts more complex features from the first layer. Third convolution layer extracts more complex features from the second layer and so on. So if the first convolution layer extracted only these edges, the second convolution layer might have extracted these legs, like that this is a leg, this is a face, this is a tail. And if there's a third convolution layer, it might have extracted that, okay, this is the entire body, this is the lower body, and maybe another layer would have identified that this is a zebra. That is what a typical convolution layer does. And then moving on, we have a pooling layer. So pooling layer has a very specific purpose as to why do we use it. So if I take this example, so the zebra is here, right? And the tail of the zebra is here. Let's say we have an image in which the zebra is flipped, where the head of the zebra is on the left side of the image and the tail of the zebra is on the right side of the image. But still, it's still a zebra, right? It doesn't matter if the tail is on the left side or the right side. It still is a zebra. So this is a problem known as translation invariance. So pooling helps images so that they become translation invariant. That is a very overview of what these convolution and pooling layers are. That is more than enough just to get up and running, right? So we have these convolution pooling layers. After that, we feed it into this flatten layer. So basically it takes care of everything that we just talked about, right? Then we flatten it into 1D array and then we pass it into this dense layer, which then does the classification. And since in according to this example, it is a multi-class classification problem, so we have used the softmax activation function. If in the example that we are going to take, it's a binary classification problem, dog or cat, right? So we will use sigmoid. You can also use binary cross entropy activation function. So some CNN applications, CNN is heavily used in image classification, something that we're going to do in our demo today, right? Object localization. Object localization basically means it helps to identify in what part of the image our desired object is located. Like it is locating that, okay, the dog is here, the dog is here, grass is here, and so on. That is what object localization does. Face detection and recognition, again, a very common feature. Nowadays, the cameras in our smartphones have this feature inbuilt. And you would be pleased to know that they use convolutional neural networks. Okay, with that out of the way, as promised, we will dive straight into the code and we would do, we would build a model, a CNN model that does the classification of a dog or a cat. Okay, so this is basically the Google Colab here, right? So as you can see, my runtime got disconnected. Okay, so what we are doing is, first of all, we are importing it from Kaggle. So I found this dataset here. I have pasted the link here, dogs versus cats. So I pasted the link of this the dataset here. So what we're doing is, first we're importing it directly from Kaggle. What you could have done is you could have installed it into your computer and then loaded it onto your Google Colab. But I found this way to be much easier. As you can see, the file is quite large. It's 1.06 GB. So I did that. One more thing, you should in runtime you can go and make it GPU. As you can see, because there's a lot of data here, and if you would train this model on a CPU, it would take a lot of time. So using a GPU would enhance your training time. Okay, so the first steps are just loading data from Kaggle onto Google Colab, and we get a zip file. So we just unzip it. That's just basic code here, right? And then we're importing the necessary modules from TensorFlow. We're importing Keras, sequential, and we're importing all the layers that we're going to use. This code here, generators, this is very important. Basically, this serves a very specific purpose. And the fact is that our training data is large. So since our training data is large, what we would do is we would divide our training data into batches. I have chosen the batch as a 32 here. So it divides the data into batches and then it feeds the data, it loads the data into the RAM in the form of batches. So one batch is loaded onto the RAM, all the processing is done. Another batch is loaded onto the RAM, processing is done, and so on, right? So this code I found it from the Kaggle documentation, right? So it just basically does that, and it basically I have written two variables here, which is training dataset and validation dataset. So we are basically dividing our data into training dataset and validation dataset. As you can see, there are about 20,000 images in the training dataset and 5,000 files in the validation dataset. Okay, then the next process is normalizing the dataset. So normalizing is important. So because our pixel values, basically images have pixel values ranging from 0 to 255. So we have to normalize it to 0 to 1. So there is an advantage of normalizing our data. It enhances our model's performance and it improves our accuracy. So it's always considered a good practice that we normalize our data. Like it's there's no harm in normalizing data. Okay. So this is the entire CNN architecture that we will be talking about. As you can see, there is this con 2D layer, which is basically the convolution layer that we talked about. And then there is this max pooling layer, which is basically the pooling layer that we talked about. So I have taken this convolution layer, pooling layer, convolution layer again, pooling layer again, convolution layer again, and then pooling layer again. So I've taken three convolution layers and three pooling layers basically. And I have done the batch normalization here. So this step, batch normalization, as you can see, I have done this for improving the trainings model. So what you can do is you can first not run this code. You can just add convolution layer and pooling layer and try and test that. I did that and my model's accuracy was coming very low. So I had to improve my model's accuracy. So that is what batch normalization does. That is why I imported, as you can see here, I imported right at the top batch normalization. That is why I imported this layer here. So I'm adding three convolution layers and then three pooling layers. So usually machine learning and deep learning, there is a lot of experimentation involved. Like one of the questions that I had was how can we know how many layers and how many kernels that we're using in each layer? How can we know that? So the answer to that is it comes with practice and it comes with a lot of experimentation. You have to experiment. You have to see that okay, if you're using two layers, if is my accuracy score coming good? If you're using three layers, is my accuracy score coming better? Sometimes it may be the case that you're using too many layers and there may be a case of overfitting, right? So it's a machine learning and deep learning is a lot involves a lot of experimentation. And that is what makes this field so interesting, in my opinion. Okay, so we have added these convolution and pooling layers, and then we are flattening it into that big, giant, one-dimensional array, right? And this code, um, one second. Okay, for some reason, it said it wasn't being able to connect the GPU. Okay, no issues there. Okay, yeah, as you can see, now it's been connected, right? Then we have the uh, dense neural network, which is basically the fully connected layer. So we're using 128 neurons in the first layer, then we're using a dropout layer. Then in the second layer, we are using 64 neurons. And in the third, which is basically the output layer, we are using the activation function of sigmoid. So when I run model.summary, this is the entire summary, right? So each image in our data set is of the size 256 cross 256. Okay. So we have 256 across 256, and that is fed into spawn booty layer. As you can see, the first output is this one, right? So the first output is this one. So as you can see, it has 896 parameters that it has to train. And then you can see, and this is all the data, the necessary data that comes out with it, right? So the total training parameters is this huge giant number. So it will take a lot of time for training. And in fact, it did take a lot of time for training. So what I did was I did the training beforehand. It took about 10 minutes to train this data set, this model basically. So I did that again. So I've used the Adam optimizer. And as I said, since this is a binary classification problem, I've used a binary cross entropy loss here. And when we run model.fit, it basically runs it. As you can see, there are 625. So there are 10 epochs we are running it for, and there is a 625, right? Okay. So important thing to note is that you can see that the loss is is decreasing, right? It started off with 1.52 and the loss came down to 0.17. We're getting a pretty decent accuracy as well, 0.92. And simultaneously, there is this validation loss, which is about 0.76, which is fairly good, right? Then we have this plots here, which is basically accuracy and validation accuracy. As you can see here, the training accuracy has been increasing, whereas the validation accuracy was fluctuating and it about, in the end, reached about 0.75, right? This clearly shows that there is a difference between the training accuracy and the validation accuracy. So this shows that there is overfitting here. Even here, right? This the difference here is showing that our model has overfitting issues, right? Again, the same here, loss and validation loss. See, the loss is decreasing for the training data set, but the validation loss has been fluctuating, and in the end, it came out about here. So yeah, I plotted these graphs for you so that we can see that there is overfitting happening here. So how can we overcome overfitting? So these are the few steps here. We can add more data. We can do data augmentation. We can add dropout layers and batch normalization. So I did dropout and batch normalization as you can see in the code above, which has improved the overfitting here. Before overfitting was pretty huge, pretty large. It has significantly reduced the overfitting here. But still, this shows that there is room for improvement in our model. Okay, so with that, our training set is done. Our training part of our data set is done. So what we'll do is we'll do a test, right? We'll feed our model an image of a dog and a cat, and we'll see that if it is working or not, if our model is being able to predict that or not. So I've done that. I've had this cat.jpg image, and when I show that, so there is this cat image, right? So then basically I'm resizing it to 256 cross 256, and then I'm feeding it into a model, right? So once I'm feeding it into a model, our model will give us a probability, right? If it is from 0 to 0.5 in the range, it means that our model is predicting that it's a cat. If it's from 0.5 to 1, it means that our model is predicting it's a dog. So it has given a value, and I'm storing that in output, and I'm running this simple if else condition, right? So what is it saying that if the output is less than zero point 0.5, tell them that it's an image of a cat or a dog. As you can see, voila, it is telling that this is an image of a cat. So we'll run it for the dog as right. We're running it for the dog, the same code again, again, again. We're now feeding the dog image here. So it runs for that again. Now it is showing that the image is that of a dog, which means the probability would have must be in the range of 0.5 to 1. So yeah, with that, this is the code implementation of CNN. I think this is a pretty good head start for you to get up and running with CNN, to see that what all you can do with CNN. Again, there is a lot of things that you can do with CNN. You can integrate OpenCV as well. And yeah, so yeah, I hope you found this presentation helpful. So yeah, thank you so much.